So we're doing section 3.2 and 3.3 together. We're going to talk about solving inequalities. And just a quick reminder, so I will tell you when we get to the part that goes in your little flip book. Just a quick reminder, when we are solving, that means we are getting the variable by itself on one side. That's what we mean when we say solve. Get the variable by itself on one side. For our inequalities, we're going to use the same rules as for equations. So that makes inequalities kind of nice, because everything that we learned about solving equations, the exact same stuff is true. We'll do the exact same things when we solve inequalities. But I'm going to say except, well, not except, there is one special rule when we multiply or divide both sides of an equation, or sorry, both sides of an inequality. I'm going to say both sides. And that's the special rule, is what we're going to write under our flap on our flip book, and we'll get to that in just a little bit. So that's, everything is exactly the same with inequalities as it is for equations. So all the stuff we learned in chapter 2 about equations is exactly the same stuff we're going to use in chapter 3. We just have this special rule. So for today, the only kind of inequalities that we're going to work on is undoing addition and subtraction, and undoing multiplication and division. So we're doing what we call one-step inequalities. We either add or subtract, or we multiply or divide. All right, so I just want to start looking at some examples. So x plus 9 is less than 12. We can think of this exactly like we think of the equation, x plus 9 equals 12. We're going to use the exact same steps. So to solve this equation, what would we do? Yeah? We're going to subtract 9 from both sides. And when I do that, these go away, and I get x equals 9. 12 minus 9 is 3. We're going to do the exact same thing here. Subtract 9 from both sides. These go away. X is less than 12 minus 9 is 3. We do the exact same thing, and our inequality, less than or greater than, comes down just like our equals does. And if we want to graph this solution, there's 3. Open or close dot if it's less than. Does it include 3? Does it include 3? It's not equal, so we use an open dot. Open dot if it's not equal. And this is everything that's smaller than 3, so we draw our arrow to the left. If we have our variable on the left-hand side here, the arrow in the inequality and the arrow on our graph point the same direction. So here we're pointing to the left. There my arrow points to the left. All right, questions there. Okay, let's look at another one. 7 is less than or equal to x minus 3. Now when we solve equations or when we solve inequalities, I usually prefer to have the variable on the left. So I'm going to rewrite this. I'm going to think of taking this inequality and just flipping it over. I'm picking it up off the page and flipping it over. So when I do that, I get x minus 3 greater than or equal to 7. The arrow's pointing toward the 7 here. It has to stay pointing toward the 7 when I flip it over. So I'm just picking this thing up and flipping the whole thing over. To there. Well, now we can think of this the same way we think of x minus 3 equals 7. What would be our first step for this equation? Yeah? Add 3 to both sides. When I do that, these go away. The x comes down. X equals 7 plus 3 is 10. I'm going to do this the exact same way. Add 3. The x comes down. These go away. X is greater than or equal to 10. And if I want to graph this, there's 10. Open dot or closed dot for greater than or equal. Closed dot if it's equal. And we want all numbers that are bigger than 10. We got the equal with the dot. So we go to the right. Since the variable is on the left here, the arrow here and the arrow here go the same direction. So our rules, when we add or subtract, it's exactly like solving an equation. There's nothing different except we have an arrow instead of an equal. All right, questions there? Okay, let's look at a slightly different example. This is similar to what we did, the example we did, or the question, homework question on the board with the problem number 58. So we want to write and solve an inequality. So let's say we have a 250 gig hard drive on our computer. And we've used 115 gig. Not 1115, 115 gig. We want to download some games. So the question asks us, what are the possible sizes for the games? So let's think for a second. If you were looking at this problem on your own, what would you do to figure this out? Yeah? We'd subtract 115 from 250. Well, that's what we're going to do. But since we're learning algebra, we want to write this out like fancy math students. So we want to get fancy. We want to be sophisticated. Well, let's say that x equals the size of the games. Well, we know that altogether, everything that we have on our hard drive has to be less than or equal to 250 gigabytes. Well, what we have on our hard drive is 115, and we want to add some more of the games. 115 plus x is less than or equal to 250. And then to solve this inequality, what are we going to do? Subtract 115. Those go away, and I get x is less than or equal to 250 minus 115 is 135 gigabytes. So this is the fancy math way that we would write what the process that we did mentally in our heads. And one of the reasons that we are learning how to write this in a little more formal way is because as the problems get more complicated, it's more complicated just to think, oh, I would just do this in my head. This is pretty easy to think, oh, I would just subtract 115. But as problems get more complicated, it's not quite that simple. And if we wanted to graph this inequality, there's 135. Is this going to be an open or a closed dot? Closed dot because we have an equal. And we need to be less than. So our arrow goes to the left, same direction as in our inequality because our variable's on the left-hand side. And there's our graph of our solution. Okay. Questions here? All right, let's get to our special rule. So on your flip book, the tab says special case negatives. So that's what we're going to write this next part under the little flap of our flip book. So our special case is if we multiply or divide both sides, so both sides is important. If we multiply or divide both sides by a negative, the arrow switches direction. So this is for multiplication and division only. When we multiply or divide both sides by a negative, the arrow switches direction. That's our special case, our one special rule for inequalities. And again, this is for multiplication and division only. So and I'm going to write a couple of these examples so you can write those in your flip book. Negative 5x, and I would put these under your little flap also just so you can see this example. Negative 5x is greater than or equal to 15. Well, if this were an equation, negative 5x equals 15, how would we solve this equation? Yeah? We're going to divide by negative 5, and we're going to divide both sides. Well, here, these go away, and I get x equals negative 3. We're going to do the same thing here. We're going to divide by -5. But we're going to think to ourselves, I'm dividing both sides by a negative, so we're going to switch the arrow. These go away, and I get x is less than or equal to -3. So my arrow switches direction. Because I divided both sides by a negative. Yes?
Can you tell me why did they make that concept of switching the endpoint?
Okay, so let's say that x is greater than 5. What are the numbers that are greater than 5?
6, 7.
So 6, 7, 6, 7, 8, dot, dot. Well, let's multiply or divide both sides by a negative. So I'm going to say negative x, and then I get -5. Is -6 bigger or smaller than -5? Smaller. -7 is smaller than -5. -8 is smaller than -5. So it's because we're thinking of taking the numbers from over here on the number line and putting them over here on the number line. So instead of to the right, they end up to the left. So we have to switch those around. And it's the opposite if the arrow are pointing the other way. If we're thinking of numbers over here on the left, they end up being over here on the right. It's kind of a mirror image kind of thing. Does that make sense?
Yep.
All right. That's a very good question. All right. Let's do another example. I'm going to say x over -2 is less than 8. This would also be written as negative x over 2 is less than 8. So if we had negative x over 2 equals 8, how would we get rid of this -2 here on this equation? How do we get that out of the bottom? We multiply both sides, and I'm going to multiply by -2 because I don't want a negative there. And I would multiply this side by times -2. Well, these go away, and I get a negative times a negative, which is a positive. So I get x equals -16. I'm going to do the same thing here. I'm going to multiply by -2. These go away. Negative times a negative is a positive. And I get x, but I need to switch because I multiplied by a negative. So that's going to be greater than -16. So I multiplied both sides by a negative, so I had to switch the arrow. All right, any questions there? Okay, I want to look at a couple more examples because there are a couple of places where it's easy to make mistakes or get confused about this rule. So let's say we had 4x is greater than or equal to -8. So if this were an equation, 4x equals -8, how would we solve this? divide by 4. And I get x, these go away, x equals negative 2. I'm going to do the same thing here. I divide by 4. Those go away. X. Am I dividing both sides by a positive, by a negative? No. Even though this 8 is negative, I'm dividing both sides by a positive. So my arrow doesn't switch. Because 4 that I'm dividing on both sides is positive. Even though this is negative, I'm dividing both sides by a positive number. All right, I want to look at one. Oh, no, I'm going to look at a couple more. Negative 20 is less than or equal to negative x. Now I want to rewrite this so that my variable's on the left. I usually like to do that. So I'm going to flip this over. Negative x is greater than or equal to negative 20. The arrow's pointing towards the negative 20 here, so it needs to stay pointed at the negative 20 there. Now I can think of this as negative 1 times x. It's greater than or equal to negative 20. How am I going to get this negative 1 away here? Divide by negative 1. These go away. Do I have to switch my arrow this time? I divided both sides by a negative, so I have to switch the arrow, and negative divided by a negative gives me a positive. So x is less than or equal to 20. All right, questions here?
How, for the first example that you showed, how did you, I just don't get it, the concept of it turning into a positive number.
Oh, that's because I forgot my negative sign.
Oh.
So it's good that you didn't get that concept because I just forgot to write my negative sign. All right, last example. And this is more just a reminder on how to deal with these kinds of problems. All right. I have 2/3 x is greater than or equal to 2. How do I want to get rid of that 2/3? Yes? We can multiply both sides by 3. So if I multiply both sides by 3, these go away, and I have 2x greater than or equal to 6. I don't switch the sign because I multiplied both sides by a positive number. And now to get rid of that 2, what do? Divide by 2, and I get those go away. X is greater than or equal to 3. I didn't switch the arrow because I multiplied and divided by a positive number. Is there another way that we could do this problem? Could I undo the multiplication and the division at the same time? What if I multiplied both sides by the reciprocal of this thing? Times 3/2 times 3/2. Well, the 3's cancel, the 2's cancel, and I get that x is greater than or equal to, I can think of this as 2/1, and I multiply straight across, 6 divided by 2, which is 3. So I can do this in 2 steps, or I can do it in 1 step by multiplying by the reciprocal. And my sign did not switch because I multiplied and divided, or I just multiplied by a positive number on both sides. All right, questions? Okay, let me stop this.